Okay, so our recording did not take again this afternoon, but we're going to try once again. So this is a review for the test tomorrow for Hobbs AP Chemistry. All right, first thing, I just want to make sure that y'all all remember that when we're trying to get the electron configuration for a transition metal, I shared this with third and fourth period yesterday, but when we're looking at a transition metal, what we want to do is that we want to have, let's say we just are looking at manganese, which is element number 25. The electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. So that's what the manganese atom would be. Now if I want to do what would the electron configuration for manganese 2 plus be, well, we know that it's got to lose 2 electrons to be Mn2 plus. So the question is, which 2 electrons are going to be lost? Well, the 4s fills before the 3d, but in terms of distance and where it's going to be farther from the nucleus. So if we have the nucleus right here, we have the first energy level, second energy level, third energy level, and then your 4s is out here. And so it's actually in farther away from the nucleus. It's going to be shielded by these d electrons, and when the energy comes in, it's going to hit those electrons first. And so as a result, even though they're the first ones in, they are going to be the first ones out. So these 2 electrons are the ones that come out. So it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, and then 3d5. And so the key is that anytime we have a transition metal, when we have d electrons, the s electrons, the higher energy level is always going to come out first. Okay, so it's going to come out of the 4. So again, if we look at a different example of this, even if we just went farther across the period and we went to germanium, GE is element number 32. It's going to be 3D10, 4P2. So it says that for germanium that it's got a plus 4. So if I did GE4 plus here, well, the electrons, the 4 electrons that are going to be lost are the ones out of the 4s and the 4p. So we'd end up with 3D10 for the GE4 plus. 3D10. Now, this is an exceptional electron configuration in that this is called a pseudo noble gas configuration. A pseudo noble gas configuration. That means almost but not quite a fake noble gas configuration here. Whenever you have S2P6D10, whenever you have the SP and D on the energy level field, that's going to be a pseudo noble gas. For all of the elements on the 4th row and below on the periodic table, that's the best they can do. They can't lose all 10 electrons. This would have to lose 14 electrons to get to have the noble gas configuration. Well, that's not going to happen. So what's going to happen then is that we form this, and that's a pseudo noble gas. That's just another stable electron configuration that atoms try to attain. So what if we want to do this, and let's just say then we have nickel. Nickel is element number 28. Well, its normal configuration is 1s2, 2s2, 2p6, 3s2, 3p6, then 4s2, 3d8. So when you're looking at this, we want to decide which of the, if we want to make a nickel, let's even say 3 plus ion, what electrons? Where are the 3 electrons going to come from? Well, we know that the first 2 are going to come from here. Okay? It's going to lose these 2. But then it's going to lose 1 here out of the D. So then it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 3d7. So you always lose the electrons out of the S first and then out of the Ds. Okay? As a result, because all of the transition metals, those in the D block, they all have 4s2, that means that this is their outermost electron. This is the one that's really determining the size. All those elements all have like a +2 possibility for oxidation state, number one. And number two, the size of the transition metals are all going to be about the same size. Because as you add an electron in, you're adding the electrons in as inner core electrons, 3d, which are closer to the nucleus than the 4s. And so they all have this 4s, and every electron, kind of these electrons shield that 4s. And so transition metals tend to be about the same size. There's not a big variance in size as you go across the period. So, two things I take out of this. Number one, when you're making an ion, they come out of the 4s, the first one's in, they're the first ones out. Number two, transition metals have nearly the same size. So that's the first thing that I wanted to make sure I reviewed with you and that you knew. Okay? The second thing is when we look at our arrow diagrams, if we look at 1s, 2s, 2p, 3s, 3p, 4s, 3d, and 4p. Okay? Now, if I put my electrons in here, let's just say we're doing phosphorus, element number 15. Okay? We're going to follow Hund's rule, which means I'm going to put one electron into each. Okay? So Hund's rule says I put one electron into each. That's Hund's. You need to make sure you know that. We also always start at the bottom and work our way up because this is increasing energy here. And the fact that we start at the bottom, that is the Aufbau principle. And then lastly, the Pauli exclusion principle it says that we're only going to put 2 electrons into each sublevel, and they have to have opposite spins. So we need to make sure we know these 3. And it's because of Hund's rule that this is paramagnetic. And even if I looked at silicon, which had 14 electrons, silicon's still going to be paramagnetic. So if I do silicon here, but if the electrons then have to be 1 into each, if they could pair up, if we did that, then we know then that this would be diamagnetic. But silicon is paramagnetic. So we know it has unpaired electrons, so it has to be like this. And so that's one of the evidences that we know that Hund's rule is accurate and true, is the fact that silicon is paramagnetic, meaning it has 2 unpaired electrons. If it's diamagnetic, then the electrons are all paired up. Now, there are only 3 groups of elements that are diamagnetic, just to review. And that's going to be group 2, group 12, and group 18. So we need to know about your magnetism, diamagnetic, paramagnetic, ferromagnetic, and that groups 2, 12, and 18, because in group 2, the S sublevel's filled. In group 12, the D sublevel's filled. And in group 18, everything is filled. Okay? So we need to just be aware of those. Now, coming back to this. This is what we refer to as the ground state. Just if we do silicon, we can just keep this as 1s2, 2s2, 2p6, 3s2, 3p2. That's the ground state. That simply means that everything is in the lowest possible energy. The Aufbau principle is satisfied. Everything's in the lowest possible energy state. Okay? That's the way we normally write our electron configurations, in the ground state, the lowest possible energy state, all the electrons. This is what it is when the light, in a light bulb, the electricity is off. But let's just say we have the gas and we put some electricity onto it and we promote these electrons up into here. Okay? Now, they don't want to stay up there. But now we have 1s2, 2s2, 2p6, 3s2, 4p2. So the electrons are in a higher sublevel without the lower ones being filled. This is called the excited state. Because the electrons are excited. Now, nature doesn't like this. They don't want to stay in this excited state. So, that's when they come back down, and when they come back down and refill into here, into the P, that's when they give off light or other forms of electromagnetic radiation. So we use heat or electricity to promote them, get them into the excited state, and then they come back down to the ground state, and when they do so, they give off light. So they absorb energy, a positive energy going up, always in the form of photons, and then they release energy on the way back down. So that would be the excited state. Now what if, though, I tried to say that it was 1s2, 2s2, 2p6, 2d, let me see, that'll be 10, 2d4. What if we try to write it like that? Well, is that possible? Well, no, because you cannot have a d on the second energy level. So this is what you would just say is an impossible electron configuration, because you can't have a d. Now, in terms of quantum numbers, why can't you have a 2d? Well, in terms of quantum numbers, if n equals 2, L can only equal from 0 up to n minus 1, which means that it can only equal 0 and 1. 0 corresponds to the S, 1 corresponds to the P sublevel. So on the second energy level, you're only allowed to have the S and the P. In order for there to be a D sublevel, you would have to have n equals 3, so L could equal 0, 1, and 2, because L equals 2 corresponds to the D. So our quantum numbers tell us we can't have a 2D, so this is an impossible electron configuration. So we have the ground state, we have the excited state, and then you just have to be aware that we have this impossible. You can't have a 2D. You can't have a 3F. Quantum numbers don't allow that. Now also then, kind of looking along the same lines, I want to make sure that you understand the terminology here. So we have the energy levels. 1, 2, 3, 4, 5, 6, 7 are the energy levels. On the first energy level, we have one sublevel, the S. On the second energy level, you have two sublevels, the S and the P. On the third energy level, you have three sublevels, S, P, and D. Then on the fourth, I don't know if you've seen a trend, 1 on the 1, 2 on the 2, 3 on the 3. On the fourth energy level, you can have S, P, D, and F. You have 4 sublevels. And then remember, on the fifth energy level, you can have S, P, D, F, and then that theoretical G, we go alphabetical after the F, the theoretical G, which really are never occupied. And then on the sixth, you have 6, and on the seventh, you have 7. So, we have our energy levels, we have our sublevels, and then on each sublevel we have a varying number of orbitals. So on the S sublevel, you always just have one orbital, one line. On the P sublevel, you can have 3, and that corresponds to your M sub L minus 1, 0, and plus 1. On the D, you can have minus 2, minus 1, 0, 1, and 2. 5 answers for M sub L, and so we have 5 orbitals. And then lastly, the Pauli exclusion principle says we can put 2 electrons into each one, and they have to have opposite spins. So on the S, you can have 2 electrons. On the P, you can have a total of 6. On the D, you can have 10. And on the F, you can have 14. So we need to know the difference between energy levels, energy sublevels, orbitals within the sublevel, and then individual electrons. So if I asked a question similar to, how many orbitals are there on the p sublevel, on any p sublevel, and the answer is going to be 3. How many electrons can be on the p sublevel? The answer would be 6. How many sublevels are possible on the third energy level? Well, the answer would be 3. You have the 3s, the 3p, and the 3d. So we need to make sure that we understand all of that. So then how many electrons total can be on the second energy level? Well, we can have 2 in the s, 6 in the p, for a total of 8 electrons. So those are all types of multiple choice questions that you need to be able to answer there. Okay? So we need to be able to understand our arrow diagrams and our electron configurations. We need to know what's the ground state, the excited state, and which ones aren't even possible. We need to be able to do electron configuration for ions as they lose electrons and know that they're always going to lose the outermost energy level first. Those are your valence electrons. Okay? Now, in addition to all that, okay, we need to, let me get rid of this. Oh, shoot. In addition to all of this, in the hydrogen atom, and we're going to come back and we're going to look at this problem. What happens, how do we write an equation for the ionization? So if I look at the ionization of Na, okay? So I know we talk about ionization energy. That means you have to put energy in to remove the electron. So when I do that then, I say the sodium atom, and it's always going to be in the gaseous state, so it's just an individual sodium atom by itself. You add energy to it, and that's going to make the Na plus ion plus an electron. This is your ionization energy right here. IE. So your atom plus energy makes this plus the electron. The plus sign indicates that the electron is separated from the sodium. So this is the equation that it's going to be for just about any element. Okay, so if I just pick, and this is for the first ionization energy, so I could pick even calcium. Okay, it's a gas. I put some energy into it. It's going to go just to Ca plus an electron. So that's the first ionization energy. Now, calcium really wants to lose another one, so you'd put some more energy into the Ca plus more energy. This would be the second ionization energy, and we'd get Ca2 plus an electron. You always take one electron off at a time. That's that chart we looked at, first ionization energy, second ionization energy, third. Now once calcium loses those two, it has that noble gas configuration, so the third energy would be very, very large. Okay? Very large, a great amount of energy there. Okay? So we need to be able to write equations for ionization energy, and that just simply means you always add energy, and then you get the ion plus an electron. It's really pretty simple. Don't try and make that hard. And then the reverse of that is the other trend we looked at, was electron affinity. So that would be like chlorine gas again, and you're adding an electron to it. Well, this time it's going to make Cl minus, and it's an exothermic reaction, meaning energy is going to be released, so it's plus energy. So this is the electron affinity. So that's always going to be adding an electron to the chlorine. Okay? So once we add an electron to the chlorine, you get Cl minus plus energy. You do that for any, and now the halogens again are the ones with the greatest amount, but even you could take sodium, if we want electron affinity, adding electrons, so we add an electron, and it would actually make Na minus plus energy. Now this value here is not going to be very negative. It's still negative. It's still going to be over here, but it's not going to be nearly as big as this one because Cl- now has a noble gas configuration, so it's very stable, which means it's going to release a lot of energy when it forms. This one is really not all that stable. It doesn't really want it. It can handle it some, but it doesn't really want it, so this is going to be a much smaller number. Now remember, there are three groups that don't want an electron at all, that the energy is actually going to be endothermic. It's going to be over here, and that's like if I wanted to add an electron to neon, I'm actually going to have to add energy here for it to go to Ne-. It's going to be a positive energy, an endothermic reaction, which means that this isn't going to be having an attraction for that electron hardly at all. It's going to want to lose it very readily and come back to the noble gas configuration because that's your stable arrangement. Okay? So we need to know the definition of electron affinity. Very, very small part of the test tomorrow, but we should be able to write an equation that simply means adding an electron. Most elements, the energy are going to be over here. It's going to be exothermic. Groups 2, 12, and 18, again, because they are the ones with the filled sublevels, they're going to have a positive value for electron affinity. Okay? So that is really, along with being able to do this type of problem, which I'm going to work for you here in a second. We need to be able to do energy, wavelength, and frequency. You need to be able to write electron configurations. You need to be able to do your arrow diagrams. You need to be able to do quantum numbers. Those are the things we need to do. Now, in terms of your Princeton review, if you want to start on that tonight, we're going to do, in your multiple choice, do them all, but you can skip numbers 1 through 4 and then 18 through 21. Do all the rest of them, but 1 through 4 and 18 through 21 deal with things that we haven't quite talked about yet, especially the 1 through 4. That's called photoelectron spectroscopy, PES, PES. Okay, we're going to talk about that on Monday after the test. Okay, and then short answer, you just need to do numbers 1 and 3. 1 and 3. And when it talks about anything that talks about PES, you don't need to know that. Okay? So, let's look then at this problem. What you need to do is copy down this problem. Is calculate the energy in joules, the frequency in hertz, and the wavelength in nanometers for the electron transition from the 4th to the 3rd energy levels in the hydrogen atom. Okay? Now what I would do is I would pause the video right now, see if you can work this out. The equations are all right here. These equations are always going to be given to you. Okay? So you don't have to know the equations, you don't have to know the constants. Now this one is not given to you, the E final minus E initial. You just need to know that. But the rest of them are all given. So pause the video, try to see if you can work it, and then when you're finished, start it back up again because I'm going to solve it for you right here. So, to calculate the energy from 4 to 3, it's going to equal the final minus initial, which is going to be, this is the final 3, the initial is 4, so it's going to be negative 2.18 times 10 to the minus 18th joules divided by 3 squared, which is the final, minus negative, and some of the students were forgetting this negative here, 2.18 times 10 to the minus 18th joules over 4 squared. Okay? So you just plug that into your calculator, and unfortunately I don't have one right here. I'll be right back. So, plugging this into the calculator, negative 2.18, second function EE, negative 18, divided by 9, minus, parentheses, negative 2.18, second function EE, negative 18, divided by 16, close the parenthesis, equals 1.06 times 10 to the minus 19th joules. And that actually turns out to be a negative number. And that negative simply means that we're transitioning from the fourth down to the third, which means energy is released. Negative always means exothermic is released. The potential energy of the electron is changed. It's going to a lower energy state, so the energy is released to the surroundings. That's what the negative means. To go from the third to the fourth, the electron is going to have to gain this much energy to go up. It would be a positive value. The only thing that would happen is these two terms would switch, and it would be a positive value. So electrons gain fixed amounts of energy, they lose fixed amounts of energy. Now when we want to go and calculate the frequency, nu is equal to E over H. Okay? So we use this. Now you can't have a negative frequency and a negative wavelength. The negative is simply showing us the direction in which the energy is released. But it's always going to be in the same wavelength and frequency. So you drop the negative sign. It's 1.06 times 10 to the minus 19th joules, divided by H, 6.63 times 10 to the minus 34th joule seconds. And so that's going to turn out to equal, just divide this by 6.63, second function EE, negative 34, equals 1.60 times 10 to the 14th. And that's going to be per second, which is the same as seconds to the minus 1, which is the same as a hertz. So this is equal to 1.60 times 10 to the 14th hertz. Now to get the wavelength is going to equal C over nu. C being the speed of light, 3.00 times 10 to the 8th meters per second, divided by the frequency. Now we just calculated 1.60 times 10 to the 14th per seconds, leaves us with the unit of meters. So we go 3 second function EE 8 divided by second function answer equals 1.88. And that should be times 10 to the second function science. Enter. 1.88 times 10 to the minus 6th. Meters. Now to put that into nanometers, it's going to go times 10 to the 9th nanometers is 1 meter. So we're going to add 10 to the 9 to 6. So it's going to end up 1.88 times 10 to the 3rd nanometers, which is equal to 1,880 meters. Pardon me, nanometers. 1,880 nanometers. So you just use this Bohr equation in order to be able to get the energy, and then use our other two equations to relate that. Now, the one other thing you need to be able to do is sometimes this is joules. Remember, this is joules per photon. We need to be able to convert that to kilojoules per mole. So you divide by 1,000 joules, you'd multiply by Avogadro's number, so you should be able to go back and forth between kilojoules per mole and joules per photon. And we had the practice problem like that. Okay? So, these are the types of problems you need to be able to do. You need to be able to answer the questions about periodic trends of atomic size, ionic size, the fact that cations are way smaller than the atom from which they came because they lose their entire valence shell. Anions are larger than the atom because you're adding electrons into the electron cloud. You get more electron-electron repulsions, so the electron cloud swells up. Basically, though, the size gets bigger as you go down, smaller left to right. Second trend is ionization energy, which is inversely proportional to that. You just need to know your two exceptions. When you go from one sublevel to the next, there's additional shielding, which causes there to be a slight decrease in ionization energy. And then when you begin pairing up, like the p orbitals, you get some electron-electron repulsions, which causes there to be a decrease in ionization energy. So you need to be able to answer questions dealing with that as well. So, anything else we will kind of cover right before class? The Princeton Review, the questions, there's explanations at the back at the end of the chapter that will explain how to do those and why the answer is the answer. And so for the 5th and 6th period, we'll take the whole first period, kind of do this again, answer any questions that you have, work on that Princeton review, and just make sure that you are totally comfortable before we take the test 2nd period. All right? Hope you all have a great night studying.